I'm pleased to announce Doug Johnstone is our speaker tonight, discussing far infrared astronomy and the need for a space-based telescope, which I've just confirmed will be part of the talk. So far infrared is the science of the cold, the old, and the dusty. And Dr. Johnstone is going to talk about the importance of this branch of light for investigations of young stars, distant galaxies, and the granular dirt responsible for rocky planets. So with that, we're also going to hear about the potential for a next generation space telescope. So please welcome Doug Johnstone, and we'll get into it.
Excellent. Thanks, everyone. I do hope you can hear me. I hate microphones, so I'm hoping that my voice projects well enough. I have to say that after I had given this topic to Reg for coming and speaking to you, my partner gave me the most amazing birthday present, which was a modern translation of Newton's Principia, which I have been reading cover to cover over the last while. I don't recommend it. It is, unless you really, thrive going through Euclid's geometry, you won't really enjoy reading Newton's Principia, and I have to admit that I've completely forgotten all of the geometry that Newton knew because we now use calculus. And on top of that, they don't write the equations out, they talk the equations out, so it's, the paragraph says exactly what you're doing. I don't recommend it, but if we do get to break for coffee afterwards or cookies or anything like that, you can ask me. There are some very interesting sections in it that were absolutely wonderful to read about, where suddenly he is actually thinking about what all of this means. And there were these beautiful nuggets of gold inside. Anyway, that's been preoccupying my time when I'm not doing research. Suddenly on Monday, I reminded myself I have to prepare for this. So let's see how it goes. The beginning of the talk, I suspect, will be background for many of you in this room because you think about astronomy and you think about the topics that come into the room. But I want to make sure everybody is on the same page. So before I get started, let me just give very briefly a territory acknowledgement. I do think it is important for us to recognize that, whether we work down here at the university, whether we work up at the observatory, whether we work anywhere else in Victoria, or in Canada for that matter, we are working on lands that didn't come freely, shall we say. And we should pay attention to the fact that there are people who have a much longer connection to these lands than we have. And as an astronomer who worked in Hawaii for a while, that is even more of a deal on the mountains of Hawaii, because the history of Hawaii is, again, a very tortured one. So I think it's important to sort of recognize that. I also, at the same time, want to recognize that I can't get anything that I get done without the support of the Canadian government, both the National Research Council that funds me directly and funds students, and the Natural Science and Engineering Research Council, which funds me through the University of Victoria for my graduate students, again, who do the predominant amount of the work. And they also fund the telescopes that we work with. So I think it's important to start there. So I want to talk about far infrared astronomy. What is special about the far infrared, right? So it lies between the gamma rays and the radio. It lies just a little bit longer than the visible and the infrared. And if you think about it for a minute, there are a number of things that you all are well aware of, right? If you get an X-ray today, they will put, a lead blanket over the rest of you so that the rest of you don't get hurt. So clearly X-rays are not something you want to have bothering you. Ultraviolet, we know, is dangerous because we all know that we put on our sunblock before we go out because long exposure to the ultraviolet is not good. Visible is where we look. Doesn't seem to be much of a problem. Why do we look in the visible? Predominantly because the sunlight is coming down well in the visible, so there's lots of scattered sunlight around. And some creatures that live, let's say, in the dark or whatever, will optimize their eyes in a different way, but for us, the visible's been good. What about this infrared? As you start to get to the infrared, when I ask students, the first thing they talk about is, that's the heat lamp, right, at the McDonald's that keeps my hamburger warm, right? Some of us might be, fancy enough that we have an infrared lamp in our bathroom to keep us warm a little bit. So we know that those are photons that can warm us, but we know they're not photons that we're worried about, unless we are worried that we're going to look like a McDonald's hamburger. And then we get out to the microwaves as we go past the infrared. And then a funny thing, because if you ask somebody about microwaves, they'll suddenly tell you, isn't a microwave oven how I heat my food? So the first four, I was moving from shorter wavelengths to longer wavelengths, and I was going to ever lower energy, and that is indeed the case. Microwaves seem to break that because I heat my food with them and my food gets hot, right? And in fact, they tell you, don't use your microwave oven if the door doesn't close properly. All of those. So we're going to come back to that because microwaves are actually less powerful than their brethren above. They are longer wavelengths, so they are less powerful, but they're special. And so we're going to come back to the microwaves at some point, okay? So just be warned that we're going to be coming back. So in general, the shorter wavelengths are the more energetic wavelengths, the longer wavelengths are less energetic, and in fact, that even works if we look at what we, in physics, will call a black body, but to you just is something that's radiating with a temperature. The hotter it is, the bluer it is, right? We're talking to people who look up at the sky, and so you all know that in your car, it should be that when you put the little thing over to blue, you get hot air, and when you put it to red, you get cold air, but the people in Detroit don't know this, right? You're smarter than they are. But blue is hotter in general, and red is cooler. Something that peaks in the blue will be hotter than something that peaks in the red. And a really nice phenomena that they already figured out early during the Enlightenment was the fact that it was an inverse relationship between temperature and that peak wavelength. So as the one goes up, the other one goes down in lockstep. The sun, at let's say something like 5,000 Kelvin, peaks at about 500 nanometers. That means if I'm at 50 Kelvin, I'm going to peak at 50,000 nanometers, which is about 50 microns. That's getting towards the far infrared. So when I talked earlier, at the beginning of my talk, I said this is the home of the cold. Now, we have a problem in astronomy, and that is we span such a large range of size and such a large range of temperatures that one person's cold is another person's hot. I work often with things that are 20, 30, 50 Kelvin, maybe up to 100 Kelvin. That's cold for any of us who don't live in Alberta, right? Remember, Kelvin is the same as Celsius, only off by almost 300, off by 273. So if you're 100 Kelvin, you're minus 173 Celsius. But that's where I work, and to me, we will talk about, well, if you're 100 Kelvin, you're warm. If you're 50 Kelvin, you're cool. But if you're a cosmologist and you're interested in the microwave background, that's at 2.75 Kelvin. Anything higher than that is warm. So as we give this talk, you're going to hear me sometimes refer to things as being warm, which are really, really cold. Just be aware of that. I'll try to come back and remind you as we go along. But the whole point is that if I want to look at something that is cold, I have to look at it in the far infrared. In fact, the light curve, the brightness of a source that is thermal, is such that as you go shorter wavelengths, it drops off like a rock. Okay? There's a really cool physics story in all of that, okay, about the ultraviolet catastrophe. But for the purpose of this, what really matters is that it drops like a rock so you just can't see it. So if you've got an object that's got a temperature of 50 Kelvin, you aren't going to see any light from it by the time you even get to the near infrared. There's just nothing there. As you go to longer wavelengths, you can see stuff, but it drops off still fairly quickly. That's what we call the Rayleigh-Jeans tail. It's the other side of what's going on, but again, the energy is lower. So you really would like to, if you could, you would always like to look at something very close to the peak of where the energy is coming out. And for the objects I'm interested in, they peak in the far infrared. That's where I want to look at. But that's not the only important thing about the far infrared. There's another thing that comes along, and that is, again, this is an audience that really understands all of that blue light is more likely to be scattered or absorbed than red light, than longer light. Okay? And because of that, we get beautiful sunsets on the Earth, and we have a beautiful blue sky from the scattered blue light that's coming down to us in other directions. If anybody happened to be up very early this morning, like I was, or like one of the astronomers up at the observatory was, we had beautiful, beautiful sunrise this morning. Isn't that a gorgeous picture? That's an actual picture of Mount Baker that was taken from the observatory this morning by Scott Roberts. But we get this wonderful reddening. Now, how does this affect us in astronomy? Well, here is a star-forming globule with the wonderful name Bernard 68, because astronomers don't know how to name things well, right? And this is Bernard 68. It's a Bach globule, and it is not a black hole. It's not a lack of stars in space. In fact, if you can look at it carefully enough, I don't think the lights are quite good here, you can actually see that there are some faint stars along the inner edge, and they're all a little bit redder. But if we use an infrared camera instead of an optical camera, we can see right through this cloud of dust. And we can see the stars that are glowing, and they're all extincted in the blue, and so we're all seeing just the red light that's coming through from those stars. Now, there's an interesting thing here. So this is optical and near infrared. We're not so deeply embedded yet, but there's an interesting thing that's happening. Remember that the dust that's in that cloud is intercepting the light from behind in this case. And some of that light is scattered, but most of it is absorbed. It's absorbed by the dust. If light gets absorbed by the dust, the energy has to go somewhere. The energy goes into heating up the dust. The dust gets warmer, the dust radiates. So it turns out that because of the interstellar radiation field, all of the light coming from stars, that the dust in our galaxy gets warmed. Now again, language is such a funny thing. The dust gets warmed until it reaches a cold temperature, such that it glows in the far infrared. So this is a picture of, taken by Herschel, of the Taurus molecular cloud. Some of you have probably looked at stars in Taurus at some point, but this is the glowing dust that's associated with the gas in Taurus. And it glows precisely because the dust is being heated by interstellar photons, by photons that are coming from nearby stars, from stars that are further away, and that gets it glowing at something like, it gets it up to a temperature of something like 20 Kelvin. Good warm dust. And when it's at that temperature, it glows in the far infrared. So, again, it's the dusty. So we've already got two of the terms that I had at the beginning. The cold material glows, the dust glows, because the dust is cold. It's a wonderful way of finding it. So there's another object, or there are other objects, and we're going to have basically the same story going on with galaxies. So these are just a couple of beautiful pictures of galaxies. The one over here, I couldn't help myself. This is a picture from James Webb Space Telescope, just reminding us how gorgeous things are that we're basically able to do with the James Webb Space Telescope. There are these wonderful different types of galaxies, everything from elliptical galaxies to spiral galaxies. Spiral galaxies have star formation going on in them. That's a clue. These elliptical galaxies in general are older, and they are just they're just stars. And also, I couldn't help myself but show this image, where on the left, it's the Hubble Deep Field that took 11 days. Okay, the Ultra Deep Field, I should say, that took 11 days. And here's James Webb looking at the same field, and it only took it about a day to get that. That's because you got so much more collecting area, such a better telescope. But you'll notice there are lots of different types of galaxies in this. I'm an astronomer. I have a friend who likes to say that a spectroscopist is a person who takes a rainbow and turns it into a graph. And I'm going to do a similar type of thing. I'm going to take a beautiful galaxy and I'm going to turn it into what we would call as a spectral energy distribution. So here is wavelength along the x-axis, and along the y-axis is, think of it as just energy coming out, the amount of energy coming out of that galaxy. And this plot is just to show you that where the energy comes out in different types of galaxies. These bottom ones, these ellipticals and disks, you can see a lot of the energy is coming out in the optical and near infrared. That's because the typical galaxy that's out there, you're seeing the stars, and the stars are bright in the optical and near infrared. However, even these galaxies, even elliptical galaxies, have a lot of light coming out in the far infrared. When you get to the more powerful galaxies, the ones that are very luminous, the starburst galaxies, and these things called ULIRGs, ultra-luminous infrared galaxies, when you get to them, look, most of the energy is coming out in the far infrared. Why is that? Why is it coming out in the far infrared? Precisely because these are galaxies where stars are forming, and stars form from gas and dust. And that means they're enshrouded by the gas and dust. Therefore, all of that energy that's coming out from the stars that are forming isn't getting to you and me. It's being absorbed along the line of sight. Think that buck globule I showed you, but think of it as being much denser, so that none of the light can get through. All of the light gets absorbed, it heats the gas and dust, and that's where we get the energy from. And so this is where we see it. So even a nearby ULIRG, even a nearby starburst galaxy, far infrared's the best place to be looking at it. That's where the energy is. It only gets bigger deal if I go back in time. The only galaxies I can see if I go back in time, because they're far away, tend to be bright galaxies. So they tend to be these ULIRGs. And they've been redshifted. So I've taken this entire diagram and I've moved it to longer wavelengths. So again, even these guys here where you say, well, you know, I might have been able to start observing them at 10 or 20 microns. That's now 100 microns, now out into the far infrared, because I've gone to a redshift of 10, where the earliest galaxies are formed. Okay? So that's why now again we have this funny nomenclature. What do I mean when I say old? What is young? What is old? You think words mean something, right? When I was a kid, words meant something. Now they don't. Because to me, if I'm looking to the end, out to the early universe, I'm looking at a young galaxy, but it's a lot further away than I am, and by now it would be a very old galaxy because it formed young. So it's all very funny language that we tend to get ourselves all confused around. This is actually a plot of the energy that comes out of the universe. So if you were just to go to some random place in the universe and calculate how much energy were you seeing, you would find that there are 3 bumps in the energy. So this is not close to a star. If you're close to a star, you're like the sun, you're going to get mostly, optical light. But if you just took yourself to a random place in the universe, this is the energy distribution of the universe. There's a fair amount of energy coming from stars. There's an equal amount of energy coming in the far infrared, predominantly from those galaxies that are dusty. So we think it's still starlight, but it's starlight that's being reprocessed. And then there's energy coming from the Big Bang. Okay? That's that 3-degree Kelvin stuff, which is why it's at an even longer wavelength. Okay? So, if you want, just is the perfect statement to start with, is that if you want to understand the universe around you, you can't do it without paying attention to the far infrared. It's at least as important as anything else. So, the far infrared is an amazing place, an amazing way to observe the universe. Great. So why don't we do it all the time? Why aren't there lots and lots of far infrared telescopes? Why isn't it the number one thing that we are doing? Well, we have a huge problem, and that is that the energy can't get down to the Earth. The energy is blocked by our atmosphere. And what is it that blocks the energy in our atmosphere? Why doesn't it get to us? Predominantly, it doesn't get to us because it's absorbed by molecules in our atmosphere. Water, carbon dioxide, you name it, it gets absorbed by the particles that are, by the molecules that we have in our atmosphere. In fact, we can now turn it around and come back to that microwave oven problem that we had, because your microwave oven doesn't heat by giving off thermal energy. It's why after you've used your microwave oven, you can put your hand in the oven and it's not hot. You can't do that with your oven. You put your hand in the oven and it takes a long time for it to cool down, right? But the microwave itself is not warm, because those microwaves, they get absorbed by water. Which is why if you put a sandwich in your microwave with a nice thin layer of lettuce, and you just put it on for a short moment and you take it out and you bite in and the lettuce burns your tongue, right? Because what you need is you need to get the lettuce, you need to get that water to then heat other things. You got to use the moisture in what you're doing to heat, because you're going straight to heating the molecules. And you're not heating the molecules a lot, because there's not a lot of energy in a single microwave, but molecules are small. So you hit a single molecule with a microwave and it still wants to bounce around a lot. It starts to wiggle and it bumps into somebody else, and that's what temperature is. And so you can get stuff very hot by just constantly poking, just like you can somebody on a swing. If you give them a good push at the right time, it's all about the resonance, you've got the right wavelength, you end up making your water hot. So thankfully we have an atmosphere. It allows me to breathe, it's got moisture, all of those other things that I want, but it prevents me from observing in the far infrared. In fact, it becomes a problem already in the infrared, but you can sort of get over it, and it becomes a problem all the way through the submillimeter. You have what we call windows, where we can see through the atmosphere between these big, big water lines and carbon monoxide lines, short carbon dioxide lines and the like. And then eventually, once you get out to the radio, you can see again through the atmosphere. So, that means far infrared astronomy is hard because I can't do it from the ground. Well, an obvious thing to do would be to do it from an airplane. Of course, this is an easy thing to do, right? You take a 747, you take a hacksaw, you cut a hole in the back of the 747, you stick a telescope in the back of the 747, and then you tell the pilot, get as high as you can, and go in a direction such that the telescope is pointed at the star you want. Now think about this, right? Think about doing it with your car. Put a telescope out the window of your car and say, now I want to look at this object. Okay, I'm going to have to drive down the Pat Bay Highway, right? And then you want to look at something on the other side. Well, now I've got to turn the car around and drive down the Pat Bay Highway the other way. That's exactly how Sophia worked. Okay? Not quite. They didn't hack the back. They have a door. They can close it. It can take off and land. This is a picture from the cockpit of the 747 as we were taking off. I got to fly on it. It was fun. The science was difficult, but it was an interesting experience. It was a very good idea. There had been a telescope like it before in a much smaller plane called the Kuiper Airborne Observatory, the KAO. This one, unfortunately, was a little bit too expensive, so NASA shut it down. I will tell you a fun story, though, because when I was on it, first thing is its call letters were NASA 747. So when we were up in the sky, I learned something, and that is you're not allowed to fly over most of the United States of America. Most of the United States of America is restricted airspace because of things like military establishments and the like, and you have to get permission for your flight path. And we were constantly talking to towers and saying, we're flying at 40,000 feet, you don't care about us, right? And they'd say, yeah, keep going. Until we crossed the border into Canada. I was the only one on the flight who didn't have to bring his passport with him, because if we landed in Canada, everybody else needed to prove that they were allowed to be here, but I would be okay. Anyway, when we got into Canada, it was Cold Lake, Alberta that refused to allow us into their airspace, despite the fact that we were 40,000 feet, which meant somebody's observing ended an hour early because we couldn't keep going in the direction that we were trying to go, and then we turned around and headed back. Very, very strange. And the nice thing about it was they could fly it. They would fly it all the way down to New Zealand, and they could use it in the southern hemisphere. It had a lot of good things going for it, but airplanes are expensive to fly, and it had to be on the ground a lot of the time. It was a tricky thing. NASA thought it was a lot cheaper than a space mission, which is true, but everybody else looked at it compared to a ground telescope, and it was hugely expensive, much more like Antarctic than it was like a ground-based telescope. So unfortunately, it was shut down a few years ago due to cost. So that's one way, and we could always go back. It's sitting around. Somebody could take it over again. By the way, the Germans were involved as well. It wasn't just NASA. It was the Germans and the Americans that were flying it. So the other thing is we put a space-based telescope up, and so this is the telescope, my love of my life as far as telescopes are concerned, the Herschel Space Observatory. Canada was involved in it. It was predominantly the European Space Agency. It was launched in 2009, a 3.5-meter telescope, which is a big telescope to get into space, and it had a lifetime of 4 years. They hoped that it would be longer than 3, but they planned for 3, and we actually managed to get 4 years out of it. What is it that means that a far-infrared telescope only lives a short time? Hubble's still up. Hubble got up into space when I was a graduate student, and I'm an old man now. So, we can put space telescopes up for a long time. It's not a problem. It's still up there. That's not where the problem is. The problem is that we are observing in the far infrared. Remember that temperature I was telling you about, right? 50 Kelvin, 20 Kelvin. If your instruments are warmer than that, they're glowing with the light that you're trying to observe. The JCMT, which I also love, ground-based telescope in Hawaii, Gerald Skeven, who must have talked to you guys at some point, he used to say that observing with that telescope was like observing with an optical telescope in the middle of the day with the telescope on fire. And you can take that statement and just double it for being in the far infrared if your instruments are warm. You need to keep your instruments cold. And by cold, I mean you need to keep your instruments at 4 degrees Kelvin or colder. You don't do that except by some type of cooling technology. And when Herschel flew, the only way we really could do it was to fly liquid helium and use liquid helium as a coolant. Liquid helium is light, right? Well, the helium is light, but not liquid helium. Helium is light, right? And you can use it for a hot air balloon, or not a hot air balloon, just a balloon, right? So that you got it. But liquid helium, you've compressed it, you've got a lot of it, it's heavy. Anything you launch costs money. So you can only launch so much. And then you want to take the telescope as far away from the Earth as possible, because the Earth is a nice hot object. You want to be as far away from it, and so you can't go up and just take some helium balloons and refill it. So you're stuck. So Herschel lasted 4 years because its helium use was a little bit slower than they anticipated, which was wonderful. That was great. So we got a longer lifetime out of it. But we only got 4 years of observing with Herschel. I want to show you some of the beautiful pictures that Herschel took. Over here on the left is a picture of the Horsehead Nebula. I'm sure most of the people in this room know the Horsehead. And the Flame Nebula just past it. The boxed region over here is a Herschel image of about that same region. And again, what are you seeing? In the optical picture, you see darkness except for a little bit of nice red where there's light coming from basically gas that's being heated quite a bit so that it's glowing. And then over in the flame, you see a little bit of gas that's being heated quite a bit. So that's high temperature stuff. But then you see this darkness. All of that darkness glows when you go to the far infrared because it's the dust that's glowing. And the next picture, hopefully, you guys will really like. Look what the horse head looks like when you look at it in the far infrared. Instead of being this darkness, it's this wonderful pillar of gas and dust. And in fact, a colleague of mine wrote a paper that said, what did the horse have for dinner? Because they found a star in it with Herschel, and they were able to see a star that was forming. There's a star forming in all of that dust and gas. And so they said, well, you know, it's forming sort of in where would be the throat, so we'll think of it as, you know, the horse having eaten something. I didn't like the title, but they did. But it's a beautiful, beautiful image. Here's another region that I've worked on in the galaxy. This is these are bubbles in our galaxy as seen by Herschel again. And these are bubbles where there's been a lot of star formation, maybe a few million years ago, maybe even a few tens of millions of years ago, and high mass stars have been formed, and those high mass stars have pushed the material in. And so you've got these beautiful bubbles that are forming. And in fact, some of these bubbles turn into chimneys and they blow material out. And you may think all of this is, you know, uninteresting, but in fact it's exactly the same physics for when you blow up a nuclear bomb on the Earth. And why a nuclear bomb, when you get it up to a certain amount of power, all the energy from the nuclear bomb goes out as opposed to going to the side, because we live in an atmosphere that is stratified. And that energy gets funneled up as opposed to being funneled this way, which is a good thing. When they were first doing bombs, they weren't sure about this, and they had to do calculations to prove that, in fact, as stupid as we can be on the Earth, we don't necessarily going to destroy ourselves. But these are beautiful, beautiful super bubbles in the galaxy. And then one of the other things we found, again, Herschel is looking at all of this dust, right? It's looking at the glowing dust. This is a picture of our galactic plane, and you can see all of these things we call filaments. And I'm going to show you a movie in a second, and that movie is going to really play to this filamentary structure that we see in the galaxy. Why do we form filaments? That was a big deal that came out of Herschel, is why do we form filaments? Why does the dust and gas not just sit there as a nice big ball, but why does it tend to form into structures like filaments? And then finally, Herschel could also look at, well, not finally, but I'll jump up to galaxies. Here's Herschel showing us some beautiful pictures of galaxies. So the picture on the top, on the right, is just an optical image. The picture on the bottom is what Herschel sees. Herschel sees the gas and dust. You put them together and you can see how they match. And you can see how the lanes, the dark lanes that you see in the galaxy, are filled in by the gas and dust when you look in the far infrared. So you need them both to get the picture. And then one more thing that Herschel could do, remember I said that we had to be in space because the atmosphere of the Earth is absorbing due to water molecules. Well, that means in space, I can look for water. I can't look for water from the ground because all I do is I see the water in the atmosphere. But if I get above the atmosphere, I can actually put an instrument on the telescope that searches for water. And we had a beautiful instrument. This is, in fact, the instrument that I was using with a team in Europe called Hi-Fi, a Herschel instrument that basically did a lot of things, but one of its main missions was to find water. So we started to find that there was water in outer space. There's water in star-forming regions. It's an interesting question of how do we get to water. You know, most things are down at hydrogen, or you might have oxygen. You've probably heard that there's carbon monoxide because the C and the O like to come together. But we actually build all the way up to water. And in fact, this is water in a comet. That shouldn't surprise you. We know that there's water, or we expect there to be water in comets. We know there's water in comets. And then we were able to show that there was water in absorption in disks around stars, that there was water in emission in the outflows from stars, and that there was water in emission in what we call debris disks, the leftover material. The reason it's sometime in absorption is that if the water is colder than the material around it, it will absorb the light. If the water is warmer than the material around it, then it emits more, which is why we see it, they're called Kirchhoff's laws. And so in this disk, the reason it was in absorption is that the center of the disk was warm, where the star was. The outer parts of the disk were colder, so as the light went through, you actually saw the water in absorption. But this was our first, this was in fact one of the purposes of Herschel, was the water trail, was figuring out how water is coming into solar systems like our own, extrasolar solar systems like our own. And then you could even go beyond. This was a project that I was only partly involved with. I didn't get very involved with it. But a project where we were looking at all sorts of interesting molecular species that could actually be found when you go to higher energy regions. And it turns out all of this is happening because of dust. So there's a wonderful joke about how dust grains, which is what we refer to as dust, grains are where alcohol forms, and we all know that grain alcohol is a good way of having alcohol, but it is on the grains that the molecules are actually able to come together. And it's on the grains that we are able to use them as a catalyst that drives us all the way up to things like methanol, formaldehyde, water, what are these other ones that they've got up here? You know, sulfur dioxide, etc. All of these things are happening on grains and then being sent back out into, as the grains evaporate, when the grains get close to stars. Okay, so thank you Herschel Space Observatory for the wonderful pictures, excellent science. Let's get on to, why do I care about far infrared astronomy? Do you know, was it the second one? I'm going to try turning, let's see if this works. Nope. Oh, nope, that wasn't the one we wanted.
Top one on the left.
Top one on the left. I want to turn these lights off. That's what I was trying to do. Is that?
Try that. No.
Nope. Okay, we're going to try one more. There we go. Okay, just for a moment, we'll put them back on. I want you to watch this movie. It's just going to take a couple of minutes. But this is a movie that was shown at a colloquium yesterday at HAA, up at the observatory. A colleague of mine who is now a professor at the University of Texas, Stella Offner, was giving us a wonderful talk about the formation of stars and the formation of binaries. And this is a molecular cloud. This is a simulation of a molecular cloud of about 20,000 solar masses. And the first thing that you're seeing is all the structure, because the cloud has turbulence. The cloud is not just sitting there, it's got lots of excess energy. And what you start to see is you're sort of wandering through it, but you should start to see these things that look like filaments as the material starts to come together along basically pathways. It basically pushes up against itself. And under gravity, you can start to see these little dots. Those are little cores that are starting to form where individual stars, and now every once in a while you're going to start to see outflows. So these wonderful stars are forming, and they create these jets which send basically little trails of material back out along the jet. I'll explain some of this in a moment, but just now I just want you to watch. You can see that there is a clustering of the stars at the center of the cloud. That's because gravity always wins, right? The only thing you can't overcome is gravity. And so you can see stuff falling in. You can see some of these, you're now seeing bubbles because the stars are getting old enough that they're basically blowing off winds or blowing themselves. Pretty soon we're going to see a supernova go off. Well, we may not actually see it, but you should see the evidence of it. There'll be a supernova that goes and you basically starts to evacuate the center of the region. Look at all of those jets coming out because of the stars that are forming. Stars that are now running around in this simulation. They're pausing it so we can go around. You can already see that there are some empty spots. And I'm not quite sure where I am in this because I've only watched it a few times. There we go. Just watch this thing through. It's absolutely beautiful. Don't believe it, right? This is a simulation. They clearly don't have the physics right yet, but they got a lot more of it than they did 10 years ago. And yeah, now you can see there's this big empty space in the middle where something has exploded out. And we are getting towards the end of the cloud because the material is going to start being dispersed. And so now you can see the big hole down towards the center where material is being pushed away. And you've got a few more stars that are still trying to form. And that's not a bad representation of what we think star formation is about. You started with a cloud. The cloud had a lot of sort of excess energy and a turbulent in sort of random motions, and yet it really wants to collapse down because of gravity. That allows you to form sheets and filaments. Those sheets and filaments get dense enough to form stars, and then when the stars form, they throw energy back through these outflows. Okay? So let me go forward and say, there we go. So from that beautiful movie, which is, I would say, the best that we can do today, this is how I like to think of star formation. This is the simple approach. We start with clumps. Those would be clumps that had formed in those filaments, and those were those dense regions. They collapsed entirely due to gravity. As they collapse, they form disks, and those disks drive outflows, and those disks also form planets. Now, something I have to tell you is that this slide is about 10 years old, and nowadays, after ALMA, we would put the planet formation stuff back at least into this one, if not into the one up there. We now know the planets start to form a lot earlier in the disks. So I'm going to jump ahead a couple of slides because I don't want to bore you with the deep physics, but basically the infall is all because of gravity. That's why things want to fall down to the center. And the reason you end up with a disk is because of rotation and because of things like magnetic fields. But I just want to point out that in that disk, you've got material coming in, you've got material spinning around, and you fire off a jet. And that jet takes away about a third of the mass. Third of the material that's coming in gets fired off in the jet. You saw in the movie how those jets looked like they had bullets, how they looked like they were going dot, 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 dot. That's actually observed. So again, this is a Herschel image. Sorry, nope, this is a James Webb image. I lied. I took this one from one of the more recent James Webb public releases. It's a beautiful one. And again, you can see these bullets in these outflows. So let me show you why they may form. And so this is, again, is a movie. This is a movie of collapse, so you're not going to see very much at the beginning because the whole cloud is collapsing and all you're seeing, not cloud, the core that's forming a single star, but you can see that it goes unstable. Because of the rotation and because it can't get small enough, the angular momentum gets it so that it goes unstable. It doesn't just form a disk. You're looking face on it, but it also forms a spiral. And that structure is an unstable structure, and it tends to feed into the center in an unstable manner, which is why it ends up with these bullets. Oops. So, we mentioned it before. In this case, the material falling in to the central star is giving up gravitational energy, right? That material, whether it's coming in from the disk or whether it's coming in from the envelope, it's falling down a potential well. That means it is got energy to give up. If I drop my wallet, you hear it hit the floor, right? Energy is given up as it hits the floor. It takes it from the kinetic energy, it takes it from the gravity, puts it into kinetic, and then it gets rid of it as heat, gets rid of it as sound, everything else. We've got gravitational energy. That gravitational energy is going to turn into thermal energy. As that material comes down, it's going to heat up, and it's going to give off thermal energy. So the way I can tell that a star that is forming, the way I can tell that a star is forming is I see the energy that's being given off. And if that star is changing the amount of material that's falling down, if that is changing, the brightness of the star is going to change. The brightness of the star is related directly to how much material is falling onto it. That's what I'm interested in. And so we produced this plot for a paper. I don't want to bore you with it, but this is how long does an event last on the bottom axis, and on the y-axis it's how bright is it. And again, some of the astronomers in the room will like the fact that I'm doing this in magnitudes. If you don't like magnitudes, look at the 2 times, 3 times, up to 100 times. That's how much brighter it is. And so you can see that we get these outbursts around young stars, everything from FU-Ori outbursts, which are big explosions of light that we see coming out, which are really related to the fact that lots of material is falling in. The reason why they look so bright is not that they're exploding outwards, but that material is falling onto them. And then all the way down, we see these various types of objects that are variable in the amount of light that they have, and they tell us that that process of forming a star is not smooth, but is clumped. Just like in the movie, you saw the outflows as having bullets in them. The material is falling in. All right, so how do I tell? Well, we go back to this spectral energy distribution I showed you earlier, and for a very young star, all of the energy is coming out in the far infrared. And if it brightens, there's going to be more energy coming out in the far infrared. And if it really brightens, there's going to be even more energy coming out. And you can see I can do something out here in the submillimeter. It's changing, but not very much. And I might be able to do something in the mid-infrared, but I'm not sure that I trust it. And we've done a lot of work on this in a paper that we just had accepted. We were looking at how well can I tell, how well can I calibrate the change in the energy to the change in the brightness at a different wavelength. And it turns out if you want to do that, as we expected, you want to be working in the far infrared. In the submillimeter, it's hard. You can get a measure, but it's hard. In the mid-infrared, you can get a measure, but it's very hard. We don't want to be working there. There's another problem if I work in the mid-infrared, and that is, even in the mid-infrared, I can have extinction effects. So, look, this object has a disk around it. All that disk has to do is wobble a little bit, and the disk gets in the way of the light. And suddenly it changes in brightness in the mid-infrared. And so something that changes in brightness in the mid-infrared may not be changing because of the change in the accretion. It may be just changing because of the change in the extinction. In other words, every time I'm sitting out on a nice sunny day and a cloud goes overhead, there's less energy coming from the sun. It's not because the sun changed, it's because a cloud got in the way. I don't have to worry about that in the far infrared because the extinction is just so much weaker. I don't have to worry at all about it as I go to longer wavelengths. So what I've been doing for the last 10 years of my life is using this ground-based telescope, the JCMT, in the submillimeter to actually monitor the variability of protostars. So these are protostars, these are light curves of protostars over about 4 years when this paper came out. And you can see protostars that are getting brighter, protostars that are getting fainter. There's one cool one up there that's periodic. It's getting brighter and fainter every 18 months. It's a wonderful, wonderful source. We've done a lot of science with it. At the same time, a colleague of mine in Korea took a mid-infrared space telescope, which is still out there taking data. It's called NEOWISE. It's taking data because it's the Near-Earth Object Telescope now. It's funded entirely to find things that might hit the Earth so that somebody like, I don't know, Bruce Willis can go up and, cause it to be deflected before it would hit the Earth. So this telescope is doing that, but very, very nicely they make the data public, and we get to use the rest of the data. And we've been finding objects in the mid-infrared that vary. And this has been really exciting, but I just want to remind you that we're nervous about how we do the calculations in the mid-infrared, and it's hard to do the calculations to go from the brightness variations we see in the submillimeter to what's the true luminosity change. We need a telescope in the far infrared. So, in the last few minutes, and I know that I'm going a little bit late, so I apologize, last few minutes, bottom line, to monitor the variability of a protostar, I've been doing it in the mid-infrared, I can do it in the submillimeter, but neither of those are where I want to be working. They're not good. I need to do this in the far infrared. We need a far infrared space telescope. For my science. We need it for lots of things, but we need it for my science. So, to quickly sum up, why don't we have another far infrared space telescope right now? Well, I have to put it in space. That's expensive. It's expensive to launch. It's getting cheaper. Things like SpaceX are helping, but it's really expensive to launch it. It needs to be big. In the optical, I can get away by putting, there was a group from the University of British Columbia that put out MOST, right? MOST was a little telescope, the smallest telescope. I think that's what they called it at times. They said, the smallest space telescope that's ever been put out there. You can put a fairly small telescope out in the optical because you get above the atmosphere and there's lots to look at. But in the far infrared, our angular resolution is horrible already because our photons are really large. Our photons are 100 times the size of an optical photon. So if I want a telescope that has the same resolution as a 10 centimeter telescope, right, I now need to be 10 meters. Oops. That's expensive. So even the telescopes that I can build, like a 3.5 or a 5 meter telescope, don't have the resolution that I want. And also remember, these photons are also a lot less energy. Similarly, every individual photon, so capturing that energy is harder. So I want a big telescope. That's really expensive. And then I need a cold telescope. That is expensive in two ways. It's expensive because it's expensive to launch the coolant, or I have to use new technology like heat pumps, which have moving parts. And one of the things we don't like to do on a telescope, anything we put in space is put in moving parts because that gives me a finite lifetime. Right? I want a telescope that's like Hubble. I want a telescope that's going to last and last and last. The Energizer Bunny of telescopes. Right? But that is very, very difficult for me to do in the far infrared. So I can't do a cheap mission like people can do in the optical. I have to build something that's going to be big and expensive, and it's just a question of how horribly expensive is it going to be. And then on top of it, I say, yeah, okay, we've all agreed that it's okay that I built an expensive telescope. It's only going to last 5 years. So this is hard. Nevertheless, we're trying. And in the last few minutes, I'll give you my sob story. We tried to build SPICA, the Space Infrared Telescope for Cosmology and Astrophysics. It was a European Space Agency and Japan Space Agency joint mission. As far as the scientists were concerned, this is a deal. We went to each of the space agencies and said, hey, we'll give you a big mission for half the cost. Because the other space agency will pay the other half of the cost. And that sort of got us a long way, but we ran into problems when they suddenly realized, both space agencies realized that they may only have to pay half the cost, but the risks and the complications and the complexity were still at that very high level. And we actually got into a competition, and then they dropped it from the competition, which was very, very disappointing for a lot of us. That was about 6 years of my life going back and forth to Europe to work on trying to get this telescope built. Would have been a beautiful thing, but it would have cost much more than $1 billion. So the next thing that came along, which thankfully I didn't have to do very much because we had everything already in hand, was the Americans every decade do a thing called a decadal report. And as part of that, NASA said to about 4 different groups, we want you to give us a concept for a telescope. So I was involved with what was called the Origin Space Telescope. It was a concept telescope for a concept of a far infrared space telescope. And the sky was the limit because nobody was building it. It was just, hey, NASA, if you gave us money, this is what we want. And I can tell you it was a lot more than $1 billion when all was said and done. It was going to be twice the size of Herschel, almost. We wanted to have a lifetime that was at least 5 years, hopefully 10 years. It was a beautiful idea. It's in the US Decadal Report, but right now NASA says, okay, thank you, but we're actually thinking of building another optical telescope because exoplanets. Everything is exoplanets right now. And it's they can get an incredible telescope that a lot of people can use for the same type of money as, you know, they're not being wrong. Far infrared is hard. So where am I the last 2 years? When the decadal came out, we were basically told that we're not going to get a far infrared big space telescope like this. Too expensive, won't happen. But they threw us a bone. They said there's this thing called probe missions. NASA launches probe missions. The advantage of them is that they're often and they're quick. Whereas something like this is probably 20, 30 years to build, to be realistic. A probe, hopefully you might be able to launch it by 2030. So we were asked, please put something into a competition. And so I was part of a telescope that was called PRIMA, the Probe Far Infrared Mission for Astrophysics, which is trying to do this for under $1 billion. And to do that, we had to jettison a lot of things, but we still want to. So the biggest thing that we did, it's not going to do spectroscopy. It's not going to look for water. It's not going to look for molecules. But it still can do the science I'm interested in. It can still do a lot of the stuff the extragalactic community wants to do. And it was one of 3 different concepts that was put forward to NASA in the far infrared. They also had some concepts in the X-ray and gamma ray. But these were far infrared. And I just have to tell you the other 2 concepts for the far infrared. Both of them were concepts to get over the fact that I really want a bigger telescope. But I can't do that because it's expensive. So the first one was build 2 small telescopes and fly them side by side and use them as an interferometer. In fact, they don't quite do that. They're not ready to fly them separately. They fly them on a boom. So they basically attach them to either ends of a boom, but they can fold that all up nice inside the launch vehicle, and then they can have it come out once it's up there. So that was one of the missions, was to be able to get up to like 30 meters by having a boom that's 30 meters and have 2 telescopes on the end. The other one is even wilder, an inflatable telescope. They've actually flown an inflatable telescope, and that one that they flew was about 1 meter or 2, and now they want to fly I think it was a 15 meter, don't quote me on that, but a 15-meter inflatable telescope. It's the dish that you want to inflate, right? You want to inflate it, and you basically, in the far infrared, you make it so the surface is nice and reflective in the far infrared, and then they need to do some active actuators to get the thing to have the right shape. But that's the other concept for a far infrared space telescope. We'll see what happens. The competition, they've just gone into the competition. We've been writing research papers. This morning I was talking to a graduate student from the University of Connecticut who were trying to write a research paper in support of this mission. But they've gone in, and we should hear, I believe in the spring, it may be not until the summer, that we hear whether or not we are successful, not to build a telescope, but whether we get successful to design a telescope. So this is a very basic study, and then they'll probably fund 2, maybe 3 designs, and then they will pick from those designs at the end of a design phase which one of them actually goes forward. So there's still hope for the far infrared, but we're in competition with X-rays, so you never know. But there is a hope for the far infrared. So anyways, with luck, I'll want to come back and discuss progress next year. So let me stop there. Thank you guys very, very much. Appreciate
There we go. I get to do my important job of being the question picker. So, questions? We've got one. Go ahead.
You may have anticipated this in your final comment, but let me ask it this way. Let's go to imaging. In your slide with the circumstellar disks,
Yeah.
you referred to ELMA. I'm wondering about, this seems to lend itself really well to an array. And I guess the second question is there some reason that an Earth-based array wouldn't be far infrared because of the cold. And then the other part of that question then would be, why is it necessary in the far infrared to be cold, but the microwave doesn't seem to quite need the same cold?
It does. You just don't need to worry about it because you don't need to launch it into space. So when you go to for telescopes, if you go to the submillimeter, those receivers are kept at very, very low temperatures. That's the part that needs to be kept at a very low temperature, right? It's even better if you can keep the whole telescope at a low temperature, but it's no help on the Earth because your atmosphere is already glowing. It's, on fire type of a thing. But your receiver has to be kept at very low temperature. So if you ever look at an ALMA receiver, for example, we built them up at the observatory. We built the band 3, 50, 64 of them for the telescopes, for each of the arrays. And if you look at them, you will see that they have stages. They have a warm stage. Then they have a cold stage, which is, let's say, at maybe 100 Kelvin. Then they have another stage, which is at 10 Kelvin. And then they'll have a 4 Kelvin stage, sometimes even colder. So, but you asked the question about why not an array on the Earth. It is really hard even to use ALMA at the highest frequencies that ALMA works at, because the atmosphere is just a mess. And with an array, you need to be able to time yourself through the atmosphere. You need to know where you're looking through that atmosphere, and you can't let the atmosphere be causing a mess of things, or you'll never get the interferometer to work. So in the far infrared, you need to get above the atmosphere. So they've tried it on balloons, believe it or not, launched from the southern United States. There's a place, Palestine, Texas, that they launched these balloons. They've been trying to do these things, but it's really hard. And so space is where you want to go. And then there's another problem, which is that interferometry is harder as you go to the shorter wavelengths. It's actually easier to do in the radio, where you can use a lot of radio technology. You can beat things against themselves, etc. And you can do with your correlators. It's a lot easier to work when you deal with an optical interferometer. So there are optical telescopes that work as an interferometer. The VLT, for example, the ESO's VLT down in Chile. But there you tend to bring all the light together and use it as an interferometer at once. Whereas in the radio, we can save the data and then do the correlation in a correlator later. In fact, in the old days, they used to put it on videotape and send it to DRAO, and they could do the correlations after the fact. So there are a whole bunch of things that make it hard. But yes, the vision of the future is interferometry at all wavelengths, I would say. It's just going to be crazy. You're not going to make telescopes ever bigger. There's going to be a size scale that you're going to stop. You're going to go to interferometry. You're going to have, you're going to do things with correlators, because that's just computers. Computers are going to get easier and easier to be doing it that way. And it's going to break the scalings that we have. But the far infrared is still going to be a mess, unfortunately. Good question.
Brian?
Yeah, well, the James Webb Telescope is a near-infrared telescope. And so I was thinking, well, why couldn't it been designed to also capture the far infrared? Which seems like it's got the properties you want.
Yeah, no, that's
cold, and it's just a matter of the instrumentation that
that is a good point. That usually when you're building the dish, when you're building a telescope, the hardest part is to get the surface for the shortest wavelength you want to look at. So that's usually where the toughest is. So in fact, you can. In fact, interestingly enough, there is an infrared telescope in Hawaii called UKIRT, the United Kingdom's infrared telescope, UKIRT. It's no longer owned by them, but it's still called UKIRT. And it preceded the JCMT. And the first detector on the JCMT was called UKT-14. And the reason was that it had been used on UKIRT when we didn't have a submillimeter telescope, and they used UKIRT as a submillimeter telescope, precisely because of what you're saying. But it wasn't good, because the biggest problem you have as you start to get to the longer wavelengths is, does your surface reflect? You may be able to make a nice clean surface, but does it reflect? You've got photons that are larger. Do they actually get absorbed? Or do they bounce off like you'd like them to? So do you have the right type of a surface? That's one. With JWST, you've also got the thing of, it was designed for the near infrared and mid infrared. It's got an instrument called MIRI. It's a mid infrared instrument. And MIRI will run out of coolant. MIRI has to be kept cold. Not as cold as the far infrared, but MIRI has to be kept cold. That WISE telescope I told you about that we're still using, when it first went up into space, it had mid-infrared detectors on it. They died after a year because it only had a plan to go and look at the sky once and be done. It was somebody who came up with a good idea. Hey, there's a telescope up there. It's just floating around in space, and 2 of its wavelengths still work. Can we get it going to look for near-Earth objects? So you aren't wrong that we could have tried that on JWST, but we couldn't have done it with the instruments that are also on JWST because they already take up all the space and they take up all the energy budget. We only have so much in solar panels. So that's why it was specifically designed to replace Spitzer, really. People call it the Hubble replacement, but it wasn't. It's really the Spitzer replacement, which was near infrared and a bit of mid infrared. So, but we could have. I don't know how good the surface is for far infrared, but you could have done stuff. The biggest thing was you'd also like to cool the telescope more. People cry when you put a far infrared telescope in space and then you don't cool the telescope because, again, your background is just so much higher. But you could have done some stuff.
You talked about what the other 2 telescopes were going to look like that were in
Yeah.
the design plan. I didn't quite figure out what yours
What would
was
ours,
going to
so
look like.
ours looked like, so that's a good point. So ours looked like the first one I showed you, the one called Spica that we had tried. It's a little bit smaller, but it looks very much like that. But the way we make it a lot cheaper is we got rid of one of the instruments. Spica would have had, actually 2 of the instruments on Spica. Spica would have had an instrument that was very much like Hi-Fi, very much like that one that allowed us to look at water and all of that. A heterodyne instrument for doing spectroscopy. Wonderful, beautiful, expensive, and takes a lot of energy. You got to run the instrument, which takes a lot of energy. And Spica also had a lot of mid-infrared instruments at the same time to complement the far infrared. And all of those have been jettisoned as well. So to try to get into that $1 billion budget, which is, it's crazy to be speaking that way, right? But in order to get into that $1 billion, so the one thing I can say, which my colleagues at NASA like to remind me, all of the movies that you went to see this year cost more than $1 billion. So just keep that in mind when we use these numbers as big numbers, right? But they are outrageously large numbers. And
Look
so
how much Otani just is being.
yeah, for example. But anyway, that's the way we're doing it is that we basically just jettisoned everything that we could to get it down. And I think we may have had to shrink the size of it down a little bit more, the mirror down a bit more.
Johnson, nice presentation. Really enjoyed that. Just changing the subject a little bit here. As an astronomer, what percentage of your time would you spend, on research versus like advocating for the next research issue? And maybe, a follow-up to that would be, would you characterize the far infrared as an emerging, maturing area of inquiry, or?
That's okay. So the first part is, it's actually really hard for me to break it down because I'm doing my research, I go to these things, I'm talking with my colleagues. When life is good, it's all interconnected. It's not always that way, but when life is good, it's always interconnected, right? And so much of what we're doing is we're able to leverage the fact that we already want to get together to talk to one another, or I'm already working on a paper on this. Can I push that paper a little bit more by writing about what do I need in order to do this a little bit better, right? And so there are others, the people who design things, they actually spend all of their life either designing something or building. And so they're going between what could I build to what will I build. And then they usually, you know, in the could, they ask me and I say, give me the best you possibly can. I have a colleague, and I love my colleague very, very much, Adrian Sinclair. He and I go for these long walks. And when he's going for a walk with me, he'll be all excited because he found a way to lower the energy cost of a readout system on a telescope we're trying to build in Chile. And he's all excited, and I immediately clap my hands and say, excellent, we can have twice as many detectors. And his answer is, you know, he's always trying to limit things this way, and I'm always trying to use what he gives me and build it more. So the people on the technology side, they, I think you would find much more of half my life maybe designing things that are never built, maybe even more than that, and the other half of my life is actually trying to build what I said I could, or what somebody told me we should be able to do. As a research astronomer, I'm really lucky. I don't feel that I break those down the same way. And so it's true that we got very involved and I was very, you know, into that telescope. But each year, if you asked how many days were fully committed to it, it was probably a week or two. So what is that, you know, 5% of my work time or something like that? It's not really a lot. A lot more I was thinking about it, but I was thinking about it because I was actively working on stuff. And it was part of the research that I was doing. Okay, so that's the first question. Hopefully that was a reasonable answer for that. The second question I think you said about would you call far infrared emerging? I'm afraid to say that I think right now a lot of us feel that the far infrared may be dying. So we had a few far infrared telescopes. We've had a few in the past. We had IRAS, we had ISO, we had Odin. We had a bunch of these small missions that people tried to do that kept proving that we should get further. We had the KAO space mission. Then they got to Sophia, and Sophia was just a bit too much, and they couldn't keep it going. And then we said, okay, we're going to go to Spica. And Spica didn't work. Well, we got Herschel, which was phenomenal. But the problem is, funding agencies don't want to build the same thing a second time. They want it to be more, for good reason, because everything is growing. But to make that jump is hard and it's expensive. And we're worried. The reason we say it might be dying is the people who built Herschel, who knew how to do that technology. It's sort of like we say sometimes about the Apollo rockets, right? That the people who knew how to do that stuff, they're retiring. If they haven't already retired, they're retiring. And so these missions take so long that if there's nothing in the middle ground, there's a bit of a fear that you will lose that knowledge and then have to rebuild it again. So I don't want anybody going home crying for astronomy. We're doing really well in the near infrared. We do well out to the mid infrared. We can still put small missions out in the mid infrared. There are a bunch of them. So following up for WISE, there's one called NEOS, which is going up there. A mission precisely to be looking for near-Earth objects in the mid-infrared. There's one called SphereX that's going up there that the Koreans are very involved with, that I have colleagues. So we can get to the mid-infrared, and the sub-millimeter's doing phenomenally with ALMA, and there are other ground-based things that we're doing. It's just this far infrared, which is the peak where we want to be, that we're struggling with. But I would say it's not emerging. I'd say, if anything, we're worried that it's actually declining. And but the problem is Earth 2.0 is not going to be found in the far infrared. That's the problem, is that it's just not that part at the moment. Yeah, good question.
Any other questions? Okay, well, are you sticking around for coffee?
I can stick around for coffee, absolutely.
Okay, so you still have a second chance, but please everybody join me in giving a